All right. So let us quickly see, like 2, 3 components that we can have. Let us say like resistor we have already seen, MOSFETs we have seen. We'll talk about capacitors, okay, because these are very important components. So capacitors, first of all, we'll talk about, ceramic capacitors, why these are important and which are the applications that it can be used for. Okay. So basically I have shown you some figures. So these are ceramic capacitors. There are different sizes in there. And then these are, like electrolytic capacitors. Okay. Polymer capacitors are these kind of things. Okay. Like these ones. Tantalum will be looking like this only. Color difference may be possible. Okay. Even these are film capacitor. Okay. So a general practice that everyone must have is, like what are the common parameters that we need to look into is like manufacturer part number, part status, which is going to be active. Okay. Manufacturer is very, very important because you have to understand which manufacturer you should take care of. I mean, which manufacturer you should focus on. Okay. Then capacitance value, voltage rating. Why voltage rating is important? That I will tell you in a few minutes. And tolerance, as we already know, like let us say if it is 1 microfarad, and if I'm telling plus minus 5%, then 5% up or 5% down it can go. So plus minus 10%, plus minus 20%, like that. So for ceramic capacitors, plus minus 10% is, like most commonly utilized. What is the technology that is used to make this particular capacitor, like whether it is multi-layer, uh, this thing, MLCC or something like that, and operating temperature and all. Just like resistors, we had temperature coefficient here also. Like basically that is nothing but a composition which takes care of, like variation of the capacitance value or its, like stabilities. So these are few parameters that were there. If you talk about, like different technologies, so we have like aluminum electrolytic most commonly used, okay, for huge higher values, like let's say 100 microfarad or 220 microfarad and all, even 330 or 470. So very high values capacitor you will not get in ceramic, okay. Then we have film capacitor, we have polymer capacitor, tantalum capacitors, all these are there. Polymer capacitors are very, very, like widely used in FPGAs circuits where, like let's say you have 1 volt requirement. So that there you need to have 4.8 volt or something capacitors you can utilize, and they will be very stable. They do not go down. Okay. We'll show it to you. So let's concentrate on few manufacturers that are there. Okay, so Visa is one of the most commonly used capacitors that is there from Visa. So Visa is there, then Murata is there, even Yagio is there. Okay, and TDK is highly like accurate capacitors that is produced by TDK. Okay, so TDK, and also if you are selecting a capacitors from TDK, you will be surprised to see that you won't be able to replace these capacitors by other manufacturers. Okay, so you have to always stick to TDK. So always, like have a practice of going little bit lower grade capacitor in your design, so that if there is a replacement required in future, let's say 5 years or 10 years later on, you can replace that with a higher, like features capacitor. Okay. And anyway, other capacitor manufacturers are like Udon is there, Kyocera is there, Kemet is there. Kemet is one of the most, like commonly used manufacturers for capacitors. And even Worth Electronics is coming up. Okay, so Worth Electronics has also a lot of capacitors available. All right. For consumer application, you can go ahead with Samsung Electronics. They have huge number of capacitors portfolio only for ceramics. Okay. So I'm talking about only ceramic manufacturers. I think Panasonic is not there in ceramics, so you can remove this. Okay. Okay. So as I already mentioned you, like we have the
Sir,
manufacturers.
you told
Hmm.
TDK is very accurate, right?
Yeah, it has very accurate and as well as very low ESR. Okay.
But
And
what I observed is it is come with a similar cost, not much difference.
I'm not talking about cost. I'm talking
Uh,
about accuracy.
yeah. What I was thinking is, what I want to ask is, so what the tech is this technology they were using is different or
Eh,
why they are able to
Yeah,
produce very accurate?
yeah. Actually, they are using little different technology, and that's how they are able to like achieve very low ESL value or very low ESR value compared to other manufacturers.
And that's their
Okay.
IP.
I'm not sure about that, but the thing that I have like come across challenges is I'm not able to replace TDK capacitors with let's say Murata capacitor. The characteristic that you see for TDK capacitor will be little better compared to Murata or Yagyu. Then what is the choice you have? You don't have any choice to replace that. Okay. And then again, you have to go ahead with a new capacitor from TDK. So this is the beauty of like TDK capacitor. Understood?
Okay. And ESR, it should be low, right? As low as possible.
It should be low, but I really do not mind it even if it is little higher and it is suitable to my design requirement.
Mhm.
Got it?
Okay.
There is no limit of going very low ESR. Like you can tell like 20 milliohm is lower for you. I will tell 10 milliohm is lower for me. Somebody will tell 3 milliohm is lower for me. So there is no limit for lower value, right? Neither the case there is no limit for higher value. So same way, what is lower, it is actually a comparative term.
What is the impact, sir? If it is high, means what is the impact of high series resistor or high series inductance? Hello.
Yeah, hi. Actually,
Sir.
yeah, there is power cut anyway. Uh, 1 second. Okay, are you able to see my screen?
No, sir.
Not visible? Okay. Okay, now are you able to see?
Yeah, now I able to see.
Okay. Bangalore is very difficult. All right. So, okay, so manufacturers, I think like many of the new engineers, they are not aware of which manufacturers are there in the world. Okay, so for them it is really necessary and really important to understand which manufacturers we should take care of. Okay,
So my question is, if it is more ESR or ESL, what is the drawback we are going to observe?
that we will see in the circuit designs. Huh?
Okay.
I'm telling you. Just wait a moment. Wait a moment.
Yeah.
So let's do the other parts first. Okay, one by one we'll go. We'll reach to that ESR ESL value. So ceramic capacitors, what we will do is we'll go ahead with like understanding of like what are the different parameters that we need to look into while selecting a capacitor. Okay. So based on description, you will understand that okay, we should have a voltage information, like what is the voltage rating of the capacitor. Then what is the value of the capacitor? What is the composition, like material that is used. Today only I'm telling you guys, most commonly used materials is X7R. Okay, little bit stable. Okay, little lower grade than X7R is X5R. Okay, and if you have to really go ahead with very good capacitors, you can go ahead with CO0, COZ or NP0. Okay, but the problem is with COZ and NP0, they are available only in like picofarad range. Okay, so like filter capacitor and all, if you need, You can go ahead with COG and NP0, but they will be lower value, not in microfarads and all. You might not get. Okay. One more thing, these compositions are not limited to this only. You have a lot of other compositions also, like YSL, or like so many are there. Okay, so don't worry about that. Okay, let's talk about package. So as low as 0201 also you can find the capacitor. Then higher values we have 0402 and 0603 and all these things up to like even higher than this, but we are going ahead written here as 2220. Okay. Now, percentage wise, if you see the tolerance, you can have 5%, 10%, or 20%. And generally, all the ceramic capacitors are SMD only. Okay. So go ahead with X7R pack, like composition always for your design. Now, one limitation will be there while selecting the capacitors is the value of the capacitor and the voltage rating of the capacitor. So for the same value, if you want to go ahead with higher voltage rating, you might not get that voltage levels in lower, a small package. So you have to have a trade-off like increasing the package size. Now always make sure that if your capacitor is available in lower size or a smaller size, choose that compared to the bigger size. Lower the smaller the size, you will find out later on that smaller the ESR value will be. Okay. So comparatively, do not tell me that okay 1 milliohm is getting lesser, so it doesn't matter. 1 milliohm is also a figure. Okay. So that's one. So a smaller the size, a smaller the ESL or like ESR values will be happening, but the voltage rating will be lesser. Okay. So, so this is the drawback, or this is the trade-off that we have to have while selecting the capacitor. Why don't I give a like example? Let us say I want to find out 10 microfarad capacitor of let us say 50 volt. You will definitely not get in 0603. You will have to go maybe 0005 or 1206. Okay. So these are the package that only will be able to give you up to 50 volt, otherwise they won't be. But if you go ahead with say 10 microfarad 16 volt, you will be able to get 0603 also. Okay, so this is what it happens. Most commonly used capacitors values are, let us say, like 0.1 microfarad, 1 microfarad, 10 microfarad, 2.2 or 3.3, or like 5.6 microfarad or 6.8 microfarad. Okay. So these numbers are there now, like 22, 33, 47, 68. So all these mm, either you can multiply by 10 or divide by 10. Both values are available. Okay. So you can do that and find all the other values available in the market. So you don't have to remember that. Many more other values are nowadays coming up in the middle also. There is no restriction with that, but these are most commonly used values. So either you go ahead with 2.2 or 22 or 220 like that. Understood? Similar to that, like 3.3, 330 or 0.33 or 0.033 like that. Okay. But you will see later on, like we have 12 picofarad also, we have 18 picofarad also. So you don't tell me that okay 12 picofarad is also available, 18 is also available. Most commonly used, I am telling a general figure. Okay. As low as like you can get 1% tolerance also for the capacitors, but generally for ceramic capacitors, blindly go ahead with 10% if there is no like drastic requirement for a particular tolerance value. Okay. So anyway, if you go ahead with COZ or NP0, they can be easily available with 5% or even 1%. But 5% should be okay for COZs, and X7R, go ahead with 10%. Okay. X5R, if you are going, go ahead with 20 also. If you want, you can go ahead. And capacitors, like are
How
very
the so how the material is correlating with the percentage of tolerance?
how
The
the
yeah
how the material.
composition. composition is correlating with the tolerance. You're saying if you are choosing
Yeah,
X7R.
yes. What happens now? Like let's say, I'll talk about X7R. Okay. So most of the manufacturers are giving you like 10%, but if you talk about TDK, they are giving X7R in 15% only, plus minus 15. So it's up to, like the manufacturers, the technology that they are utilizing and giving you the tolerance of the capacitor that they are producing. If you go ahead with lower tolerance, your cost might increase. That is the only thing. And there is nothing like X7R is not having, like 20%, or X7R is not having 5%. X7R can have 5% also, 10% also, 20% also. It is not the material dependency. Okay. But most
Okay.
commonly used values, I am telling you that 10%, 15% you can go ahead.
Okay.
Voltage rating, I told you already. Now, here a very important thing that I'll tell you about voltage rating is, let us say you have a regulator that you have to design. Here, let's say 5 volt, here, let's say 3.3. The capacitor that you will choose, let's say at the output, is even if we keep my capacitor voltage rating greater than V out, it should be okay. So as low as, let's say, 4.8 volt is sufficient. So I can choose 4.8 volt rating capacitor. All right. Now, now this will have a problem. Ceramic capacitor, actually based on bias rating, its value actually decreases drastically. So if you see bias rating, it goes like this. So this is the bias voltage. Let's say it is like 0, 1 volt, 2 volt, 3 volt. So at 3.3, it would have reduced to, let's say, 70% or something. So whatever value you are keeping, let's say 0.1 microfarad, 70% of that only will be remaining. So are you okay with that? You go ahead with this voltage rating. But my suggestion is for 3.3 volt, 4.1 microfarad capacitor, go ahead with 16 volt minimum, or 0.1 microfarad, never choose 16 volt, go ahead with 25 volt or 50 volt. Okay. So this is very common practice, like go ahead with 50 volt all the time. I'm very easily available, most abundantly utilized. Now coming back to 5 volt, same 0.1 microfarad you can utilize with 50 volt rating, because both side you don't have to change it. Okay. But if you have to be very specific, if you have to be very specific, you can go ahead with 0.1 microfarad 50 volt this side, 0.1 microfarad 25 volt this side, because it is lower voltage. But what if you have, like let's say 48 volt input this side, then you cannot go ahead with 50 volt. What you have to choose is 0.1 microfarad, 100. Okay. And this is not the case for electrolytic capacitor and all that I'll tell you later on. Like you don't want to go ahead for 3.3, 50 volt for like electrolytic capacitor. You might need just 16 volt is more than enough. Okay. Or for higher values of capacitor, let's say 10 microfarad you want to use, or 22 microfarad you want to use. You don't want to waste a lot of money by choosing a high voltage rating capacitor. You can go ahead with 10 volt even, or 16 volt also. So that is more than enough. So higher the value, the lower voltage rating also doesn't matter. But lower the value, this bias rating changes drastically. Okay. So that's the difference. I'll show you just after this. Let me give you a proper, like table that is taken from one of the product TDK. So you can see like we have, like operating temperature. So COZ and NP0 both are like almost like minus 55 to 125 and 150. Now X5R is up to 85 and X7R is there here, which is going up to 125. So that's what I told you. Like X7R are most commonly used capacitors, which is having a very nominal operating temperature range also. But this is not the a specific value for all of this composition, just an example. Okay. So you can see X7R, X7S, X7T, X8R, X8L. So all these, different temperature coefficients capacitors are available with you. They have given you, like capacitance change also. So when no voltage is applied, X7R is giving you plus minus 15%. Okay. Whereas X5R is giving you almost there that only. But mostly I have seen like X5R will be having little more tolerance compared to X7R. Okay. Yeah, you can see here, based on vibration, what is the capacitance change? So you can see based on the temperature characteristics, the change is this. Based on voltage characteristics, change will be some other. Okay, based on delta V, delta C will change. Based on delta T, temperature, delta C will change, and based on vibration, also there will be a change in capacitance. So all these are different parameters that you have to look into while selecting a critical capacitor. Okay. So with vibration itself, you are seeing plus minus 2.5% change is happening. And for these guys, plus minus 7%, 7.5% is happening. So what are the different parameters which is causing my capacitor value change? Even if you have a 10 microfarad capacitor, you cannot expect this to be 10 microfarad in all the conditions. Based on temperature, it will change. Based on like voltage applied, it will change, and based on vibration, it will change. Okay, understood. And mostly in all the cases, the value will be reducing only. They have given plus minus, but vibration might increase plus, but generally voltage and temperature it reduces. Let me give you one example. Yeah.
Sir, during soldering, whether
Mhm.
manually or free flow or in time, it is
Okay.
generally like 300, 350, 400. So when in data sheet, the specification tells it's like 125, 150. But during
Mhm.
the soldering procedure, it will be 2x, 3x times. So won't it
Mhm.
cause problem?
It won't cause problem because you are not operating the capacitor at 300 degrees centigrade all the time. It has a capability like it will withstand 300 degrees centigrade for, let us say, 5 minutes. Okay, so within 5 minutes you will be able to solder the capacitor. I don't think 5 minutes is
Yeah, that's
like
that's too
yeah,
easy.
even that is even less, very very less than that will be the temperature 300 degree at the capacitor. Even if you do manual soldering, it takes maybe, let's say, 20 seconds.
Yes.
You
Less
won't be
than one.
applying 300 degrees centigrade more than 10 second, 20 second. Okay. You'll immediately remove the tip, right? So, so this is how it is saved. Okay. Let me give you an example of, a capacitor that I have taken, like 100 nanofarad, that is 0.1 microfarad, most commonly used capacitor as a decoupling capacitor value. Rating is 16 volt X7R plus minus 15% and 0002. Okay. So there is something called as impedance characteristic Z. Okay. So the impedance characteristics, what is happening is based on frequency, my impedance in changing almost 1 kilo ohm to going as below as how much? Let's say 20 milliohm. So 20 milliohm is the least value that is there at what is the frequency here? Can anybody tell? 20, 30, 40. Let's say, I think it is 10, 20, 30. 30 megahertz.
25.
Yeah, so almost 30 megahertz it is happening, like the least value. And again, it starts increasing. So this is the impedance characteristics. Impedance characteristic is different from the ESR characteristics that I will tell you. Let's talk about ESR. The ESR is completely the real value. Okay, so the real value you can see almost 20 to 30 ohm is there here. Okay, so 30 ohm is there at 1 kilohertz. Now, as my frequency is increasing, it is going as low as 20 milliohms. Okay. So this is the least value that you can get for your capacitor. What capacitor I am showing it to you, this one, that one. So same graph you have to see for any capacitor that you are choosing in your circuit, and try to understand like if it is having lower value, or one more thing is the variation graph. You see this much is varying. This is the biggest problem of ceramic capacitor. You know, NP0, if you see, those will be happening like this almost. Very less change. Okay. So that's the beauty of those capacitors. Understood? Even tantalum capacitor will show better graph for ESL compared to ceramic capacitor. All right. And then, you know, like with frequency, what happens is the capacitance change. So capacitance change, it was almost same from 1 kilohertz to let's say 10 megahertz. Okay. And then it increased drastically to 10 microfarad. So see, same value capacitor has become 10 microfarad at a very high frequency. So is your application going to go up to 10 megahertz or 20 megahertz? That you have to take care of, because the capacitance value will change. And if that capacitance value is going to put your circuit into unstable state, so those things also you have to take care of. Like I'll teach you the LDO. In that case, I'll tell you like if you know, like you are going to put let's say 1000 microfarad output capacitor, your output might get unstable. Okay, because the poles will be outside the unity circle. Okay, so so these are the problem that happens, and this will be causing just by using this lower value also, because their value is increasing. Like zero point 0.1 nanofarad, 0.1 microfarad I have used, but it has become 10 microfarad. Why? Because the frequency has changed. Understood? Mostly for DC output or DC input voltage and all, it will be like zero frequency. So this graph will not be applicable only. But due to, you know, like ripples or sometimes what is that? High transient responses and all, you have to take care of the frequencies. This is what I was talking to you about the bias. Okay, so let us say I have used 0.1 microfarad, that is, you know, like 100 nanofarad capacitor. So at 0 volt bias, you are having complete voltage. But let's say your application was for 3.3 volt. So what will be the volt, you know, like value that will be remaining with you? 3.3 somewhere here. So it will be around 92 nanofarad. So around reduction is 8 nanofarad. Understood? So this is the problem with ceramic capacitor. Higher the bias voltage, your value is reducing like anything. See, it was rated for 16 volt. At 16 volt, you are seeing not even 50%. It is less than like 40 nanofarad. So you do not tell me that you are using 0.1 microfarad capacitor, let's say 16 volt, and you are going to supply 15 volt, you know, like voltage. So you will not be having 0.1 microfarad at all. At 15, it will just remain 35 nanofarad or something. Got it? One more graph I'll tell you. It, you know, like for temperature characteristics. Okay, so based on the temperature variation, no bias means there is no voltage applied. Okay, so when no voltage applied was there, what happened is 100 nanofarad was almost more than that at minus 50 degrees centigrade. And as my temperature is increasing, let's say this is 25 degrees centigrade. So 25 degrees centigrade is 100%. But with increase in temperature, my value is reducing. But there is no drastic change. Like 125, it was, you know, like rated. So at 125, it is becoming around 85 nanofarad. So just 15 nanofarad change due to temperature rise. But with DC bias and with temperature effect, you can see DC bias is 8 volt applied here, and you can see this. So I'll tell you quickly. This is the capacitance page that I had opened it, and I have taken the data from this. And in this one, You can see you have impedance curve, ESR values. If you want, you can download them or take as a like picture or all those things. And if you want, you can do the graph settings also, whether you want it logarithmic range or linear range. So linear, if you do and apply setting, it will be linear. Okay. So linear is not proper for frequency variation. That is a big problem. Okay. So log graph is always better. Okay. So that's all. This was all about, like capacitors, ceramic capacitors. You have capacitance change based on frequency, DC bias. You have some other characteristics also, ripple temperature rising and all, but that is not a problem for us. That is not a scope for us right now. Okay. So you can see this is the capacitor, which is, let me just open it. This is which type it is? Yeah, COG. Okay. So COG capacitors, I told you that variation is less. Okay. So let me give you a quick introduction of this one. So if you go ahead, impedance curve, let's say impedance curve. So what is happening? This is 50 ohm, and then it is going up to 100, like 100 milliohms. Okay. Where is ESR? ESR, just like this one, just like this one. Where is ESR? Yeah, ESR is drastic change, you can see here, but in COG, ESR is very less change. Okay. Understood. And DC bias characteristics, this is what is the most important part about the COG. Like if you apply voltage 0 volt or 50 or 60, whatever it is rated for, any voltage you apply, the voltage, value will remain same. It won't change. So this is the most stable capacitor because of the DC bias. So this is the biggest change for COG capacitors. Okay. You can see here. The DC bias is giving you worst result compared to COG. Understood? So you will be overwhelmed to utilize COG capacitors in every place, right? But that is not a possibility. It is very costly, and its value is limited to like a few microfarad range maybe, or like mostly it is picofarads, okay, or nanofarads, not even microfarad, okay. All right, so this was all about the capacitors. And you can see temperature variation also. Let's say there it was almost 15 nanofarad change, but here it is from 100 picofarad. It has just 99 picofarad. Less than 1 picofarad change is there for complete temperature. The graph may look very wide variation, but actually the variation is very, very less. Okay. So this was the beauty of NP0 or COG capacitors. Okay. All right. So this was all about ceramic capacitors. Any question? Ceramic capacitors values are limited up to, like mostly 100 microfarad. Very rarely you will get, okay. Like up to 22 microfarad people can use it. Even 47 these days are coming, but a stack up, okay. So you can see pictures will be there like this. Where is it? Yeah, see this one. So these are stack up capacitors. Two parallel capacitors are put to make to achieve higher values. So that's the understanding that you should have about the ceramic capacitors. Okay. Let us quickly see the electrolytic capacitor. So same few manufacturers. I'll just tell you quickly. Like Visa is one of the most important, like guy for ceramic capacitor, and Panasonic is mostly preferred for automotive components and all. And Nichicon, Rubicon, and Chemicon. These three, and even Chemet. So these 3, 4 are very, very specific for only for the electrolytic capacitor. But these days, Panasonic is winning the world, okay, winning the market. So you can always concentrate on Panasonics, and they have come up with polymer capacitors type in electrolytic format, okay. So that also you can take care of. Same. Most commonly utilized tolerance value will be like, let's say 20 microfarad, sorry, 20%. And electrolytic capacitors are utilized only for achieving very high value of capacitance. Okay, so like let's say you need 220 microfarad or 470 microfarad and all. So for those values, you won't get other than electrolytic capacitors. That's the reason, these are used. A little bit limitations are there for them, like they have a lifetime. They are not, running complete, I mean, very high, long lifetime. So it is number of hours, something like that. I'll tell you. First of all, we'll talk about voltage rating. So you can go ahead with, let's say, up to 100 volt, or, like 150 volt, or 220 volt, or even, 470, 480 volt or something. I'm not sure whether this is a standard value, but 330 volt will be there. Okay. So most commonly utilized in digital circuits are like 35 volt or 63 volts. Okay. So these two values generally I utilize in digital circuits because there your voltage rating will be maximum 24 volt. So even 35 volt will be sufficient for that, or if you want, you can go ahead with 63. So 63 volt is much more common compared to 50 volt. Okay, that you have to understand. Now, one thing is there with like electrolytic capacitor is it is a polarized capacitor. It means, let's say you had the regulator and here it is, let's say 24 volt output, and this is the capacitance and this is the ceramic capacitor. So ceramic capacitor, any direction you put, no problem, it is unpolarized. But this electrolytic capacitor will be polarized. Okay, so you have to take care of this positive and negative terminals. They cannot be put any direction. Okay. And ESR value, why the problem with electrolytic capacitors are, their ESR value is very high, like 1 ohm or something, or 2 ohm or something like that. So what do we do to reduce the ESR value is, in addition to electrolytic capacitor, we try to put parallel ceramic capacitor. So this will actually equivalently reduce the ESR of my circuit. Okay. And you are telling now why ESR is important. So let us say this ESR is there, right? So there will be a, if higher the value of resistance, there will be a voltage drop, I mean, current flowing through that, and there will be a power dissipation across that. Okay. So that we do not want to. So that's why we do not, we try to take care of lower ESR values. Operating temperature same. Mostly you will get up to 105 or even 125 you'll get, but cost will increase drastically. But ceramic capacitors were bit higher side. Okay. Part status would be active, and application are mostly general purpose consumer electronics or industrial it is used. Automotives are also available, but will be little costly. Ripple current, they can withstand very high ripple current. That's the beauty of electrolytic capacitors. Ceramic capacitor will not be able to withstand very high ripple currents, but these guys have the capability. Okay. And it is actually measured in the form of frequencies. So like 91 milliampere for 120 hertz. This is just a specific value I'm giving you. It is not true for all the capacitors. Okay. And at higher frequency, you can see you have little higher ripple current. So how much ripple current it can withstand, that is also a good feature for capacitor that you are choosing. Because with ripple, the value will reduce. Okay, so that is there. Dimension, if you talk about this electrolytic capacitors.
Ripple current means pulsating, means AC component in DC.
Yes. About the dimension, if you talk about, mainly the capacitor will be there. So what is the lead distance between them? That is your lead spacing. So it can be like, let's say 5 millimeter or 10 millimeter or even 12 millimeter. So like that, even 7 millimeter will be there most commonly. values. Size is diameter. This complete value is diameter, and what is the height? Okay. So based on the height and diameter and the lead spacing, you can choose the dimension of the capacitors. So you will see for bigger value of bigger size for the same value of capacitor, the cost will be lower. And if you want a smaller value of the a smaller size of the capacitors, your price will increase. Okay. Mounting type, I mean, two kinds will be there. One is surface mount and through hole, both are there. So through hole capacitors are utilized just because to withstand the vibration requirement or something like that, because it should not fly off from the PCB, because they are a bit heavy also. As I was talking about lifetime, so let us say I'm giving you an example of 2000 hours at 105°C. So if you are running your circuit at 105°C, the capacitor that you have put is going to run for 2000 hours. So it can be like, let's say 1000 hours also at 85°C, or in these days of people are designing up to 5000 hours or even 10,000 hours. So like that they are reaching. Okay. Now, the beauty of this particular number of hours that you are seeing is, don't think like it will give me, let's say I'll talk about 2000 hours. So 2000 hours at 105°C. But if you see the graph, temperature characteristic graph at 25°C, this will run for 5 years. Okay. The number of hours will be 5 years into, or you convert it to hours. So the temperature is causing the life reduction. Okay. So that's the understanding. Let me take a capacitor. Let's say I'll just take this one. Okay. So you have aluminum electrolytic capacitor, and you can see what is that. The voltage rating code is there, like 6.3 volt, 10 volt, 16 volt, 25 volt, 35 volt, or 50 volt. You have the diameter and height. Just now I told you, like what is the diameter and what is the lead spacing. So all these things are there. P is the lead spacing right now. Here you can see. Okay. Then where is the values? Yeah, here. Part number explanation. So this is the product like EEE. Then we have series code FP, or this thing. Then we have voltage rating. So you have to write down 0J for 6.3. Similar to that, if you want 35, you have to write it 1V. Okay. Then what is the value that you want? Let us say if you are writing 220, it means it will be 22 microfarad. Similar to that, up to 1800 microfarad is available. If you want to write 182, it will become 1800 microfarad. Okay. And yeah, that's all. So these are the things that you have to take care while writing the part numbers. So it is always good idea to go ahead with DZ key and find the part number. Otherwise, in the data sheet, they have given complete part numbers with different capacitance and different ESR values and their size and all. So size, case size, you can see you have like a diameter and lead spacing. Okay. So they have given you vibration proof product also. So if you want to see like 100 microfarad, we have without vibration proof component and with vibration proof components. Okay. So these are the voltage rated capacitors. Okay. Now let me take you to the product page here. So Panasonic is one of the most important company, or like a very nice company for the capacitors. So you can directly go ahead to home page, and you can see we have where is the capacitors. Capacitors. Okay. So we have polymer capacitor or electrolytic capacitor. So polymer capacitors are there very nicely. This one. And, hmm. So you have they have come up with hybrid capacitors these days. Okay, that's what I wanted to show you guys. So they have come up with conductive polymer, like hybrid capacitors, and these hybrid capacitors are very nice. Okay, and I have used in many equipments also. So you can see. So they have rated voltage, let's say up to 25 volt to 63 volt, and it depends on the series, completely. Like it is not that any series will be giving you this voltage only. So hybrid capacitors, I think I have seen that they are limited to around, like 63 volt or 50 volt only. They are not able to give you higher voltage ratings. Okay, like like 220 volt and all, they are not able to give you. Okay, and they are already rated for 4,000 hours at 125 or even 135 degrees centigrade. And they have very higher ripple current capabilities and low ESR they are telling you, but it is like even, I mean, less, just close to 1 ohm. Okay, not very less than that. Okay, so this was all about the electrolytic capacitors. Any question like why do we use electrolytic capacitor or why do we use ceramic capacitors? So only one change you can tell, that for higher values of capacitors you can go ahead with electrolytic capacitor, and for lower values of capacitors you can go ahead with ceramic capacitor. If you have to save space, you should go ahead with ceramic capacitor. One more advantage of ceramic capacitor is their lifetime is almost infinite, you can say. Okay, so they do not fail, but electrolytic capacitor will have a limited lifetime. Okay, if it is running at higher temperature. So this is the main difference that is there. Okay, other type of capacitors we will see later on. Like I'll send you the materials so you can have a look. Let's take let us talk about fuse. Okay, or shall we take LDU? What shall we take next?
Sir, when we should go with the tantalum, sir? In these two, I got it. The difference. When we should choose tantalum or that one.
One very good reason for going for like tantalum capacitor will be, let us say you have to have a very high value of capacitor requirement. Okay, let's say 100 microfarad or 220 microfarad and all, and very low voltage rating. Let's say 4.8 volt or 6.8 volt, something like that. You can go ahead with tantalum capacitors. Like in FPGA applications, sometimes what happens is we need to have very high value of capacitor because of low voltage output. Okay, like there we have 1 volt output. So 1 volt output, if you put this, electrolytic capacitor of 330 microfarad, so you won't get a very good result. And FPGA requires, around a 2% output tolerance. So for that, this might not serve you the very good purpose. So there is the beauty is going ahead with polymer capacitor or tantalum capacitor. Okay.
Polymer, sir. What you told one more?
Yeah, polymer.
Okay. So at what time we have to choose one polymer over tantalum or vice versa? Is there any difference between them?
These days actually polymer capacitor, I'm sorry, this tantalum capacitor has one more disadvantage is they break. Okay, like if you put your hand or something firmly, they will break. So in that case, they have come up with polymer capacitor, which is little costly but better. Like they have little better capability, mechanical strength compared to tantalum, and they have higher accuracy also. Like they do not change. Okay, so let me just show it to you. Capacitor. So you have, like under polymer capacitor only that, what is that? Tantalum will be figured. Okay, so see, tantalum is there here, and polymer aluminum is there, aluminum polymer is there, and hybrid electrolytic and all is there. So if you see this one, they will be very costly. Nowadays, like this tantalum capacitor are getting off the shelf from the market, and they are coming up with polymer technology. Okay, because they were breaking it, and they are trying to reduce, remove them from the shelf. Okay, so let me give you one example. Let us say, yeah, let us say one of the capacitor. Let's say I'll take up. Yeah. So you can see this is the conductive polymer capacitor, and the rated voltage is just 2.5 to 6.3. So just now you saw that if I use ceramic capacitor for 6.3 volt rating, you won't be able to utilize for very, like wide range of bias, right? But here they are telling you 2.5 to 6.3 volt rating only, and capacitance range, see how high it is, 100 microfarad to 330 microfarad. So this is the beauty, like you will not be able to get it ceramic capacitors in this high value range. That is the only reason we go ahead with uh, polymer capacitor. And you can see, let's say 2.5 volt rating. So you will have to use it for 1 volt application, maybe. Even if you want, you can go ahead with 6.3 volt also for 1 volt or 1.5 volt application. And mostly like processors, and they need these capacitors. Okay. Okay, so polymer capacitor, I think you have now a little bit better understanding.
Life, sir, life, how good the life is.
Life is better. Like you can see here, we have mentioned like endurance is 2000 hours for at 125 degrees centigrade. But the problem is, you will not be using 125 degrees centigrade. So you can utilize it for like even years and all. So there is a graph, like I could not show you. If you see let me just show it. Do you have any? Let me see one data sheet and show it to you. The how characteristic is, like there. So based on the temperature, the characteristics changes. Okay. I'm not sure if they have given that characteristics into the data sheet. Yeah, that is not there. Let me just see it here. Yeah, sorry. Let me just see it here. How to select a capacitor is capacitor. Go ahead with see, tantalum is there separately. Tantalum polymer is there. So instead of tantalum, you can go ahead with tantalum polymer. But for very high-end application like FPGA boards or processor boards or ADCs, DACs, those kind of application, you can go ahead with this. Otherwise, for general application like consumer and all, you can go ahead with this tantalum, which will be little less costlier compared to this one. And go ahead with aluminum capacitors. You wanted to talk about the lifetime, so we'll take one of the like capacitor. Let's say third, how much? 47 microfarad I'll choose. 20% I'll take. Voltage rating I'll take, let's say 35 volt. A number of hours, if you want, I can take, let's say 2000 hours for 105 degrees centigrade. 125 is how many? 16 only. 1000 hours is 14 only. Leave it. Like only one is enough. And let me take the people like Kemet is there. Nichicon is there. I was telling you. Then we have this. Okay. Let's take these three companies. So that particular, like let's say I will take this particular capacitor, and even I don't know whether Nichicon has given the graph. So all these three will see whether they have given the graph for the timing. So see, in this temperature stability characteristics and expected lifetime calculation chart. Okay. So now you see here how the timing changes is they are saying that at 105 degrees centigrade it will run 2000 hours. Okay, you see 2000 hours is here. Now when the temperature reduced to 85 degrees centigrade it has become 20,000 hours. And if your temperature is just 65 degrees centigrade, it has become 2 lakhs hours, 200,000 hours. So you just see how many years it will come. So 2 lakhs hours, right? Divide by 24, that many days, and divide by 365, that many years. Okay, so continuously this many years it will run. Got it? At 65 degrees centigrade. Divide by 24. Divided by 365. So it is coming around 22 years. Okay. Got it. So you will never, it will never fail if your application is requiring, 65 degrees centigrade environmental temperature. Understood? So very first sheet only you got the calculation. So Camet is also a very good company, and Camet has been bought by Yageo. So Yageo has become a leader in all these components company. They have acquired almost everybody. They have acquired now Camet, they have acquired AVX. So AVX Kyocera, that was called as. And Yageo has become the superpower, I think. Okay. Any other question? Part numbering is there. Then let me go ahead and show it to you. You guys must go ahead with
For
data sheet and try to
resistors,
understand what we have.
there is a automotive standard, right, for resistors called AEG. Similar to that, for capacitors also, there is any standards?
Yes, AEC standard is there. AECQ 101, I think, or mostly. Yeah, AEC 101 will come. Let me just check here. Rating is it is general purpose. Okay, so rating is not there. If you want automotive, they will be giving you like let's say what value capacitor you want to choose. Let's say ceramic capacitor you want to choose, or electrolytic. Automotive grade.
Yeah, anything will be fine.
Okay, let's talk about ceramic. So if you talk about ceramic, and let's say my choice is 10 microfarad capacitor, 16 volt. Okay, so 10 microfarad I'll just go ahead and choose. So yeah, it is there. Then we will take 10% ratings. Okay, 10% tolerance. 16 volt I told you guys, so 16 volt will take. And that's what I will tell you here. Automotive grade is there. Okay, so AECQ 200, not AECQ 101. Okay. And then we have package. So since this is 10 microfarad, I told you like you will not be able to get at 0603 package, or it is available. So you can go ahead with 0603 package, or better for 10 microfarad capacitors. You can write it down, make a note that try to go ahead with 0805 always. And if you have higher voltage, let's say 25 volt, then you can go ahead with even 1206. Okay, so this is how it is better. 10 microfarad, don't go ahead with 0603. It will be very like DC bias characteristic will be very bad with this one. DC bias characteristic just now I showed you that with voltage applied, the value decreases drastically. So in these higher packages, that will be little stable compared to lower package. Okay. So this is how it is there.
In renewable sectors, like I mean to say
Yeah.
for in gate driver boards and so on. So, is there any standards they are used for capacitor selection?
I'm not didn't get your question. What is that?
So for automotive industry, there is a standard AEQ. Is there any other standard for especially for renewable sector like the solar?
No. It's like all
That's
industrial grade
related to.
capacitor will be sufficient for them. Okay. So you can go ahead with industrial grade. Otherwise, if you want, you can go ahead with AEC Q200. And nobody is stopping you to choose an automotive component for using into industrial grade application. Okay. So in industrial application also you can utilize automotive grade components. So you can see we have TDK here, and this is there like 16 volt X7R 10%. Low ESL. This is the problem with this TDK guy. So equivalent series inductance is low, and these guys, all other companies, they are not giving that. So that's the reason you are not able to replace your TDK by other companies, like by other companies. Got it? So this was the change. Okay. So this was all about the capacitors. Now what? Let us quickly go ahead with linear regulators. Okay, so linear regulators just now we have seen. It all depends on your package, which package you are going to utilize in linear regulators. So I think let's do that linear regulator. It is going to be a little longer topic. Okay, and we will design some regulators also. So let's take up maybe next session. So what I will do is I will post this, all the component selection PDFs into the group, and I hope you can, like take